Well, welcome to Math 3163. We are getting into the section 1.1, the first section of our textbook and stuff. And again, I want to remind you the textbook we are using is the Abstract Algebra, an introduction by Thomas Hungerford. So here's the book, and again, we're starting with section 1.1. And if you remember what me talking on the other video about the syllabus, we're going from section or chapter 1 all the way up through chapter 6 in our textbook for our Math 3163 course. And our focus is going to be on ring theory. But before we get there, we're going to start out with a couple of topics here. Again, easing you guys in here because honestly, the folks that end up taking Math 3163 Modern Algebra are math majors, folks that are double majoring in math or minoring in math, also math education folks. So we typically start this stuff out with your comfort zone because this is going to be a math proof class. There's going to be lots of symbols and stuff and a lot of writing. So first off, the different types of numbers. Now, if you go back in history, the first type of numbers you'll run across are what we call the natural numbers. Natural numbers, also known as the countable numbers, they have a symbol of a double-backed N there, and the natural numbers are 1, 2, 3, and you keep on going forever. Now, later on, talking about historically, we had to add the concept of none, which was 0. So the next type of numbering system you should be familiar with is whole numbers. Now the whole numbers are the natural numbers plus 0. So the whole numbers are 0, 1, 2, 3, so forth and so on. Okay? Now, whole numbers typically do not get some kind of mathematical symbol. But beyond that, we start getting into some major symbols in here. And then the next one was the concept of the negative numbers. You know, you lend somebody $5, now they owe you $5, so that's the negative number. Or temperature-wise, it's really cold, the below zero concept. And those are called integers. The symbol for integers is a double back Z, and integers are ... -3, -2, -1, 0, 1, 2, 3, so forth and so on. Now, beyond integers, we start getting into what we'll call fields, and in terms of your countable numbers, the idea is the rational numbers. The rational numbers symbol is Q, we'll double back Q there, and the rational numbers are by definition where you have a fraction, an integer divided by an integer. And remember, you can't divide by 0, so the denominator will be all the other integers except 0, of course. So examples of the rational numbers will be everything from -2/3. 1 is an integer because it's 1 over 1. You can make it a fraction. 7 halves, 1/3. I mean, they're not really in any kind of order, but any kind of way you can write an integer over an integer. -7/8, so forth and so on. So positive and negatives, plus or minus on top or bottom. Now, we have something also called the irrational numbers. Typically, there's no symbol for irrational numbers. I've seen some textbooks that have a double-backed I or IR on it, but basically, it is all the numbers that you can't write as an integer over an integer. The irrational numbers are never-ending, never-repeating decimals. Things like pi, square root of 2, negative the square root of 3. Square root of 4 doesn't count because that's 2, but all the things that you cannot write as an integer. Because when we put the rational numbers compared to with the irrational numbers, we also get a numbering system called the real numbers. Now, you should be very familiar with that. The real numbers, symbol for that is the famous double-backed R, and that is basically the rationals and the irrationals put together. That is the rationals union irrationals, and that's all the different kind of numbers you can think of. Dot, dot, dot. They go on forever. You got everything from negative the square root of 3 to let's see here, 0. Pi is an irrational number. E is an irrational number. 2.71828. Pi 3.141599269. Okay. Square root of 2. I mean, these things go on forever in the typing. I did not put them in order, but you get the idea. It's both of these two numbers put together. Also, 2/3, negative 2/3, 5/8. They're all put together there, including the 0, so forth and so on. But you think you're done with the numbering system, but you're not. We can start expanding this, and we have something called the complex numbers. Again, you should be familiar with that. And complex numbers, a symbol for that is the famous double back C. And what you got here is it's in the form of A plus BI. I representing that square root of -1, where A and B are real numbers. And I represents the famous square root of -1, and which is the imaginary aspect of this thing. So the complex numbers, imaginary numbers, same thing. So what we're going to be working with in this chapter 1 and focusing on it is because it's a great place to start with the concept of ring structure and the structure of numbers is we focus on integers. So in chapter 1, we're going to be focusing on integers because integers are a very interesting group of numbers because you can add them, integer plus integer is an integer. You can multiply them, integer times an integer is an integer. You can subtract them, integer minus an integer is an integer. The problem you're going to come across is the famous division. An integer divided by an integer is not necessarily an integer. It's actually a rational number. So you can add, subtract, and multiply, but not necessarily divide. And that's the problem with the integers and the ring structure. It's the division we'll continue to focus on. So as we focus on the integers, we have something called the well-ordering principle, and it's just a concept. And when we talk about mathematics, a principle, it is a statement of truth, axiom, principle, pretty much same thing here. The well-ordered principle says this: for every non-empty subset of non-negative integers contains a smallest element. So as long as they're non-negative, you can always get a smallest element. Well, what would the smallest element be? Well, if they're non-negative, well, it's going to be 0. If 0 is not in your set, then try 1. If 1's not in your set, then try 2. Go all the way up. Eventually, you're going to hit at something that's going to be in your set. So every non-empty subset of the non-negative integers will actually contain the smallest element. Now, some of the other things that we're going to be focusing on, again, with this concept of division is actually dividing. So how do you actually end up dividing? Well, if I give you an example, let's talk about dividing for a second. So I'll put my little page over here and talk about dividing, which is my problem here. If I take 161 and I divide that using old symbol notation here, divide that by 32, what's my answer going to be? Well, we're going to go old school on this one. If I got to take 161 divided by 32 and I don't have my calculator with me, well, I'm just going to have to use old long division here. 161 is my dividend. My my divisor is 32. My quotient goes over here, and maybe or maybe not, I'll get a remainder. So let's see here. Let's see here, 131. So how many times does 32 go into? Well, it doesn't go into 116, so it's going to have to go into 161. So how many times does it go into 161? I'd say, let's try 5 times. 5 times 2 is 10, so put the 0 there, carry the 1. 5 times 3 is 15, plus 1 is 16, and I subtract, and I get 1. Since there are no other numbers, this is the remainder, this is the quotient, this is my divisor, and this is the famous dividend. So how do we end up writing the answer? Well, the answer is 5. The problem is you got a remainder. So typically we would write the remainder part as a fractional part of the answer. It'll be the remainder over the divisor, 1 over 32. And that's the answer. It's 5 and 1 over 32. Well, that's a problem in writing this because, hey, you got a rational number here, and you actually don't have just integers. So another way we can write this thing out is this. So let you know, this was written in the famous, this is the quotient, basically plus the remainder divided by the divisor. But another way we could have written this answer is this. We could take the quotient, so the dividend, write it as an equation. The dividend, which was the original answer, the dividend is equal to the divisor times the quotient plus the remainder. Now you look at this thing going, well, isn't that pretty much the same thing? Yeah, it is, but it's not. Let me explain. The dividend in this problem was 161. That's what we were dividing into. The divisor was 32. The quotient was the answer 5, plus the remainder was 1. But as I've written this out in this format, called the division algorithm, by the way, we'll get there in a second. As I've written it out in this particular format, I'm no longer using fractions. I'm no longer using rational numbers. Each component in this equation is an integer. So this, when you divide, is how you can write it without actually using fractions on the thing. That's going to be the big key. We're going to be using the division algorithm. So if you turn the page over, that is what Theorem 1.1 is in terms of your textbook, the division algorithm. The division algorithm states this. Let A and B be integers. Welcome to the wonderful world of modern/abstract algebra. We let letters represent numbers here. So let A and B be integers, with B being greater than 0. Then there exist unique integers Q and R, such that A equals B times Q plus R, and R has to be greater than or equal to 0. Well, we use Q and R for a reason. Q for the quotient, R is the remainder, but the remainder has to be greater than or equal to 0. Now that's key right there. Because A and B are integers, nowhere does it say that they can't be negative except right here. You can't divide by 0, and when you're dividing, you want to divide by a positive number. You'll see why in a second. So, if I did this one right here, if I just did, what is 14 divided by 3? These are positive. So this is 14 is my dividend, 3 is my divisor. So I'm going old school of long division here. 3 goes into 14. Let's see here. 3 goes into 14. How many times? Let's see here. I believe 4 times, and 4 times 3 is 12. And then I subtract, and I get 2. And since I don't have any more terms, here's my quotient, and here's my remainder. So I would write this answer, 14 divided by 3, in terms of the division algorithm. It is 14 is equal to the divisor, which is 3, times a quotient, which is 4, plus the remainder is 2. Just putting in that format. B is my divisor, 4 is my quotient, plus the remainder 2. 2 is greater than or equal to 0. However, what if I did this? What is negative 14 divided by 3? Now we know that negative 14 divided by 3 is the same thing as 14 divided by negative 3. Positive divided by negative is going to be a negative. Negative divided by a positive is going to be a negative. But the way the division algorithm works, whatever you're dividing by has to be greater than 0. So I have to write it like this. Negative 14 divided by 3. Now, if you try to do it this way, you end up messing it up. Let me show you. 3 into, quote, negative 14. And most people would do it the same way. They would do 3 times 4, and I'll write it out. So they'll put 3, and they'll make it negative. 3 times 4, negative 4. Negative 4 times 3 would be negative 12. But remember, you're going to subtract, which changes your signs. That puts it a plus. And negative 14 plus 12 is negative 2. And then they would tell me the remainder is negative 2, and my quotient is 4. And that's absolutely wrong. And the reason why it's wrong, and this is where most people would make their mistakes at, is the remainder has to be greater than or equal to 0. So to be able to do this problem, I'm going to take 3 and divide it in negative 14, but it's actually going to go in there negative 5 times. Remember, you want the remainder to be positive. So negative 5 times 3 is actually negative 15, and then in your long division you would subtract, which changes your signs. It becomes a plus. Negative 14 plus 15 makes it a 1, but that's positive 1, and that's my remainder, and it's positive. So negative 14 divided by 3 written in terms of the division algorithm would end up being negative 14 is equal to your divisor, which is 3, times negative 5 plus the remainder, and your remainder is 1. So that is the division algorithm working with negatives. You've got to think that, remember, you've got to make sure the remainder is positive. So if you did it this way, you would be wrong negative remainder, but increase it by one more in the negatives, and typically that would make you, add to the negative and make it a positive number down there. So you kind of have to outthink how to do negatives and stuff. But the most important thing is running it in these formats of the division algorithm. So what I want you to do is go in your book, and on section 1.1, I want you to look at problems 1, 2, 3, and 6. Just look at them and try them out. These are not to turn in. These are just problems out of your textbook that I want you to look at and get the feel for this particular material. Now, when it comes to stuff that I want you to turn in, I will declare it to be a homework set. I will type it up, upload it onto your Canvas site, make you print it out, and then you write up your problem and proofs or your calculations accordingly and stuff like that. These are just problems to look at and to do, but don't turn in. So this is section 1.1. We'll move on to my next video, which will be on section 1.2.